Hey everyone, and welcome back to the Foundry by Forge College. First off, a massive congratulations to all of you. You just submitted your capstone final, whether you tackled the detailed timeline or that deep dive essay, you have officially crossed the finish line for that module. That is seriously no small feat. So as we continue our journey through blockchain fundamentals, and specifically the Introduction to Blockchain Technology course, we are shifting gears a bit. In today's explainer, we're taking everything you just internalized about provenance and moving it from the abstract into the mechanical. We are exploring the foundations of distributed systems together.
Because let's be real for a second. Verifiable provenance absolutely requires distributed architectures. Think about it. The entire concept of provenance, tracking the undeniable verified history and origin of a digital asset, completely falls apart if you're relying on just a single fallible authority. Imagine one single server sitting in a damp basement somewhere holding all the ultimate truth. Some guy trips over the power cord to plug in a vacuum, or worse, quietly decides to edit the database, and boom, your provenance is totally gone. It's meaningless. That is exactly why we have to take the basic networking fundamentals you already know and use them to build systems that don't rely on just one machine. We have to distribute the trust.
Okay, let's take a look at the blueprint for today's explainer. We'll be covering the setup, ledgers and nodes, twin metaphors, the four-node drama, and we'll wrap up with trade-offs and takeaways. Let's dive right in. Part 1. The setup. Core concepts. So what exactly is a distributed system? Well, as you can see sketched out here, it's basically multiple autonomous computing entities, which we call nodes, communicating over a network to achieve a shared goal or present a unified service. To you, the user, it just looks like one seamless, magical application. But behind the scenes, it's a massive team effort. The big shift here, compared to what you might be used to with a standard single-node server, is the decentralization of control. No single computer is the undisputed boss of the whole universe anymore. And because of that, we introduce something pretty wild called partial failure modes. In a normal setup, if your server crashes, the app is down, period. But in a distributed system, one machine might literally be on fire, another is somehow disconnected, while three others are just happily processing data. Architecting around that partial failure is the entire game. Moving right along to part 2, ledgers and nodes, vocabulary and actors. Meet our star player, the distributed ledger. Now this is a very specialized type of distributed system. It's a replicated state that maintains an ordered record of transactions across nodes, all without trusting a single operator. I want you to mentally separate the broad underlying engine, which is a distributed system, from the specific vehicle you're driving, which is the distributed ledger. You see, distributed systems can be used to replicate almost anything: configurations, caches, multiplayer game data, you name it. But a distributed ledger is a very specific application pattern designed to keep a permanent, ordered history of events that everyone can verify independently. But who is actually maintaining this ledger? Well, that brings us to nodes versus peers. A node is simply a running process with its own local state and communication interfaces. It's any machine playing a role. But a peer? That's a node with roughly equal rights in a peer-to-peer setting. And this brilliantly illustrates how architectural choices literally change everything. If you're just a node in a traditional client-server setup, your job is super easy. You just talk to the boss server. But if you're a true peer, suddenly addressing, discovery, and routing become entirely different beasts. You have to figure out how to find other peers in the wild, who's allowed to talk to whom, and how to route messages fairly without a central switchboard guiding the way. Part 3. Twin metaphors, mental models. Because thinking about network packets bouncing around the dark void of the internet is, well, kind of abstract. Here are 2 grounded scenarios to help us really grasp network unreliability. The first is synchronized notebooks. Imagine you and your friends are sitting in completely different rooms trying to maintain an identical notebook of expenses. Every single time you buy something, you write it down and send a photocopy to everyone else. For the notebooks to match up, you all have to agree on the exact order of the expenses. If you apply updates in different orders, your balances are going to completely disagree. So this metaphor solves the ordering problem. Our second metaphor is the postal system. Imagine sending those updates to your friends via a terribly run, totally chaotic post office. Letters get lost in the rain, they get delayed for weeks, the postman accidentally delivers the exact same letter twice. The postal system focuses our minds on the reality of dropped packets and node crashes. It teaches us how to design systems that use tracking numbers and retries, patiently waiting in reconciling state. Now, what's really interesting about this technical table is how we systematically counter those postal system disasters using our notebook rules. We architect around inevitable failures using 3 key properties.
First, replication. That means maintaining multiple copies of state. If one database replica crashes, no big deal. Another one has the synchronized write locks. Second, partial failure. This is when that one server crashes while the rest of the cluster is totally fine updating the system. And third, consensus. This is the holy grail, folks. It's the agreement on an ordered sequence of events. When our network is acting like that chaotic post office, we use consensus mechanisms like electing a temporary leader to force everyone back into the synchronized notebook reality.
Part 4. The 4-node drama, replication and failure.
Okay, to see this in action, grab your popcorn because we are going to anthropomorphize a tiny little cluster of 4 nodes drawn out here. Let's call them A, B, C, and D. Here is how our mini play unfolds. Step 1. A client wants to increment a counter from 42 to 43. They send the request to node A, who is currently acting as our brave leader. Step 2. Node A writes this down in its log and sends a quick message to B, C, and D saying, "Hey everyone, update to 43. Nodes B and C immediately persist it and send back an acknowledgement. Now, since A, B, and C make up a majority, the system commits the change. The counter is officially 43. But wait. Step 3, what about node D? Well, poor sleepy node D crashed right in the middle of the operation. It literally fell asleep at the wheel. But the beauty here is that our majority quorum safely incremented the counter anyway. The system didn't just freeze up and halt. Step 4, eventually node D wakes up. It realizes it missed the meeting, contacts its peers, reconciles its missing logs, and quietly updates its own counter to 43. Drama resolved. But let's add a serious plot twist. What happens if there's a literal network partition? Imagine a physical cable gets cut and suddenly nodes A and B are totally isolated from C and D. Neither side has a majority anymore. The system now faces a brutal choice: safety versus availability. This is known as a split brain scenario. Do A and B refuse to process any more transactions so they don't accidentally diverge from C and D? That ensures consistency, sure, but it halts the entire system. Or do they keep accepting writes independently to stay highly available, knowing full well they will have to reconcile those conflicting, diverging states whenever the network is finally fixed? Every single distributed system out there has to make this hard choice. Part 5. Tradeoffs and takeaways. Design choices. Understanding these dynamics isn't just academic theory. It's exactly what we will be engineering together as we progress through the rest of the learning tracks in the Forge College ecosystem. So let's review our golden rules. First, replication and coordination are the absolute essence of these systems. The moment you move from single node to distributed, you are permanently in the business of coordinating copies. Second, fault tolerance is architected, not accidental. You don't just get lucky when node D crashes. You survive because you purposefully built a quorum system to handle it. And third, every single design is a trade-off. You are constantly balancing latency versus durability and consistency versus availability. The crucial point here is that things like quorums and leader elections aren't just fancy buzzwords. They are deliberate engineering levers that have entirely predictable effects on how your system behaves under stress.
As we wrap up this explainer, I want to leave you with a rather provocative question to chew on before our next session. We just saw how a leader like Node A can keep order, but who was responsible for ordering writes when nobody trusts the leader? What happens when all the nodes are peers, and they suspect some of their fellow peers might actually be malicious? That question is exactly what drove the historical evolution of consensus mechanisms, and it's exactly where we are heading next. Thank you so much for joining me for this explainer. To dive deeper into this subject and explore a whole range of other fascinating Web3 topics, be sure to head over to forge.college. Keep building, keep questioning, and I will see you in the next one.